Hello and welcome to the walkthrough through the 30 filters for image processing 2013. Alright, the first I'm going to show you is the ACOS image filter, which let's take from the top. Just is the first filter we're going to go through, so I'm just going to mention everything there is. First off, I'm defining the width of the capture screen to 420 pixels and the height of it for 240. These are essential in order to, the next couple of lines is essential in order to actually create the whole, what's it called, webcam show. And the same here, output is the output we're going to use as in our camera. And we are width, multiply with height, multiply with 3. And 3 is the GL-RGB. That means there's going to be colors in it. Alright, next up here, VidGrabber update necessary in order to display the video. The if statement VidGrabber, we're gonna make a new frame and we're gonna call a new integer total pixels, which is the same as the output. It's just displaying the window. And another unsigned char, which is pixels, which refers to the VidGrabber get pixels. Got a number of pixel numbers, small, cosinus, and verse. Here we are going through, we're making a for loop which goes through every single pixel there is. It's starting from 0, then I becomes greater than. If I is less than total pixels, which total pixels was the frame or of the camera, it should add another one to I. So that way we're gonna go through each and every pixel there is in our camera. First we're gonna set our pixel number to the value of pixels. Then we're gonna take the ACOS of something. We need a low number, therefore we're gonna divide it with 100. Then we're gonna take our ACOS for the pixel small. Then we're gonna multiply with 100, which what is we're gonna be using for the output. As you can see here, our pixel inverse equals pixel cos, and as you see here, our input for I, which is every single pixel in the webcam, is equal to pixel I, pixel inverse, sorry. So that's it, right here, I'll start. Going down here, here's how we're gonna actually draw the whole webcam. It's gonna refer to something above, like we did VidGrabber and video texture is referring to something up here, so we can actually create the webcam. So let's see how it looks like. And we got our normal picture on the left, and we got an ACOS filter on the right. As you can see here, it's sort of like the inverse, but with slightly dark colors. My hair, pretty awesome. So yeah, it's my hair is normally brown, light, so on, so on. Alright, that was first out of 30. Then it's auto contrast. It's automatically contrasting the color that is inside. Again, this isn't really important. Let's go down to the important right here. We are assigning red, green, and blue pixels to this. These are something you're gonna see throughout the entire video. Which is basically red, green, and blue. Again, we're assigning them different kind of math stuff. It's necessary. Alright, so here we got the contrasts. So if red is bigger than 100, then the red should add another 20. So it's like 120. And if it's below 30, then we should minus 20. And so forth with green and blue all the way down. This right here is taken partially from a website and a video, and it's necessary in order to actually make the contrast. So just follow that, and it's actually working. Again, we're drawing the webcam right here, and let's see how it looks. Yeah, as you can see here, might be a bit messed up, but you can actually, yeah, we got a filter where we actually add something, and Yeah, you can see the color is much more bright. See here, pretty awesome. Boundary detection. Alright, we are doing the whole thing again. Assigning new outputs. This time we're gonna use 3 outputs for in order to get boundary. We need to make it a grayscale image, and then we're gonna take erosion of that, and we're gonna minus the first output with the erosion, and then we're gonna get our boundary detection. That way we can delete all the fillers inside and only get the edges and boundaries of the picture. Alright, so right here, defining red, blue, and green again. The for loop, which will go through our each pixel of our picture. And if our red is bigger than green, and green is plus 10, and if red is bigger than blue, plus 10, red should turn white. If not, it should be black. And we define output 2 as red. As you can see here. Erosion. Erosion is actually where you take an object and make it shrink. That way you can actually cut through the picture and get a more sharp image and see the edges more. So we got a for loops which will run through the picture, and then we got our sum for it, which is as you can see here, we define sum as a floating number. The floating number is going to be sum plus our output divided with 255. So that's when it's going to go. So if our sum is equal to 49, it's going to be black, and else our output window number 3, at this erosion, is going to be white. Or the other way around, sorry. If sum is equals 49, it should be white, and the other way around, it should be 0. Then we're gonna do our boundary detection. Again, a follow to go through the window, red, green, and blue, and then the most important line right here is our output window 4, which is our boundary detection. It's gonna take our first grayscale or black-white, whatever you want to call it, minus our erosion, and then we get our boundary detection as stated in our image processing book. And here we draw everything else. Let's see how it looks. So as you can see here, black and white, sorry. First picture right here, we see that we take and just differentiate between our color image and just take them to black or white, as you can see here. Depending on where the light hits, my face is gonna be. Well, then we're gonna erase it with 7x7. It's gonna be a lot messier, so we can get the edges, like the clean edges, and then we're gonna boundary it, so we're gonna only highlight the edges, and everything inside is gonna be removed. So that's what's happened. Normal webcam, the first black-white, erosion, and boundary. So erosion is actually an image between these two, and then just minus these two together, or minus these two, and we get the last one right here. So yeah, that's one. Brightness. Again, set everything else. Pixels right here. We go through our total pixels. This the web camera again, as you see here. Then we outside chat pixels. Then it comes a new one in pixels. Yeah. It just goes through every pixel, and if I is greater than total pixels, which is, I don't know, then the new pixel, then the pixel it is on plus the brightness, and we got some new bits. That's not really most important. The most important is down here. As you can see here, if we go with key up, the brightness is gonna be plus with 1. If brightness gets above 100, it's just gonna stay at 100. So can't get more than that each pixel. And if you just press key brightness 1 down, it's gonna be -1 down. Let's see how it looks. As you can see here, does nothing at all. So what we're gonna do is we got that for loop right here. If I press up, just keep pressing up. So you see my right picture right here is gonna get brighter as every time this for loop is running through and through every time I press the key up, and it's gonna take the pixel plus brightness. So brightness is gonna be add +1 every time unless it comes to 100. So that's the maximum. And then yeah, you can see here it just keeps on going. There's nothing much left, and there's the maximum if each pixel comes, there's a boundary if it can go above 250 and or below 0. That's brightness. Closing. Closing is where you use dilation first to expand it, and then to expand and make the edges more round, like making it sharper, and then you fill out the holes by expanding everything using dilation first. You fill out the holes, then you erase it afterwards, and then by using erasing after dilation, you get the lines or edges, so it's gonna look like a perfectly good image, and that's a way you can filter images that is unsharp and needs to be filtered. So again, seen this before. That's more important is the dilation right here, which goes through everything, and it just it adds white pixels to it. So if the sum, you see here our 40 goes through everything, x and y. Our output again is the sum, blah blah blah, like before. The more important stuff is the if statement here. If the sum is equal or greater than 1, it should be a white color, or else it should be a 0 color. Mostly just white, so it's going to expand a lot. After that, we're going to use erosion on it, and it's going to narrow it down like we saw it before. And let's see how it turns out. So as you can see here, the first picture is dilated. Next is erosion. And then we're gonna take those two and put it out in our output. The erosion actually refers to our dilation output, and then it changes to our output 4. So it's this first, dilation, then erosion, and then we actually got our wanted filter, which is closing. Color depth, increase and decrease. Again, seen it all before. Standard loop for loop. This is the formula for changing color depth for red right here, and then the colors will be changed in the if statement. Then we got for green and blue all the way, and our output is going to be the new colors as you see here. The first red, green, blue. As you can see here, output 1 for regular red as upstairs. Upstairs is the new R, G, and B. So that way we can actually increase or decrease the color depth, as you can see here. By pressing a key up or down, we add value 8 to the color, or -8. Let's try one more time. I'll try it. I'm gonna press up. Oh, there's a lot of blue colors in this. As you can see, I'm gonna press down, and there's a value button right down here. It's thanks to a video I saw on YouTube. A simple color filter, red. It's not much to say. You define each red, green, and blue like before, right here, but except except that this line right here states that our output should be the input of blue. So let's see how it goes, and it goes red. So that's it, basically. It's because all the others, green and blue, is 0, then the only thing that actually matters is red. So that's the only color there is, except for slightly different kinds of red and stuff like that. So yeah, easy filters to do. Not much to say. Color tracking binary. Again, set the whole thing up, make a loop. We got 4 loops to run through our picture. This should be changed right here. Sorry, I'm gonna age that. Alright. We're defining red, green, and blue, and then in this statement we're gonna determine if blue value is larger than red and green. If the blue value is larger than red and green, it will output pure white, and if not, it will output black. So let's see, I got a blue sweater on today, so it should be working somehow. As you can see, the blue sweater dominates everything, so that means my filter works. Alright, awesome. Next on the left, contrast. We just had auto contrast, now we got contrast. It's basically the same, except I can use my up and down keys to actually define everything. As you can see here, the same, except for the if statements above. That was for the autocorrect. This is just auto contrast. This is normal contrast, where we can use up and down to actually differentiate between each stage of contrast by plus and minus 10. And let's try it one time. Go up and go down. Going up and down. So this is actually a much better contrast compared to the other, because yeah, I'm not that good. Crop. Yeah, you just have to crop the image from large to smaller, and we're gonna again define everything up here. Video grabber, if video grabber. Then right here we're gonna define our Y, where it goes for height and width, where it's this for loop is regular just run through, but this one will output our output image as cropped. So we are multiplying it with 0.3 in order and 0.6 in order to actually get a cropped window. So let's see how it looks. As you can see, you can only see my eyes. I can just do like this. Compared to over there and that one there. So that's a cropped window, and it's basically all because of this, because you divide or multiply it with 0.3 or 0.6. This is actually the only thing you define red, green, and blue, and outputs again red, green, and blue, so it just looks like a normal weapon except it's cropped. Dilation for 7x7. We just had that in the others, but let's just take a look. Again, we're gonna change everything as to white and black colors by looking at red. If red is bigger than green plus 10 and red is bigger than blue plus 10, then it will make them pixels white, if not black. Same again for loops with a float sum, and the float sum should be divided by 255 in order it shouldn't exceed 255. That's just the way we can do it. The next one right here, this is basic neighborhood processing, which takes the given value of a pixel in a neighborhood of 7x7 and checks against the parameter below. Then it outputs the neighborhood in total white or black if the center pixel meets the either parameter. So we got a sum again, like before. This one should as you can see right here, the first picture, normal black and white, like we got before, and the same last one here, dilation as we had before. Yeah, works the same way. Divided with 255, so we get a sum between or 0.000 something and above 1, just so everyone is clear. So it's not because one is just an imaginary number. We can actually divide with something else, but it's much easier, and the internet says so. Erosion disk 5x5. A disk is a circular object where you got 3 on the vertical and 3 on the horizontal, maybe like some sort of star. It's a neighborhood again. We do the same as before. Like erosion, we got the same as erosion. Oh, sorry, dilation, the result before, where the sum equals to the other, and we define our disk right here, plus 10, plus 2 in the y space, and plus 2 in the x space. That way we like cross our disk if you want to. It's only a 5x5 disk, and it's divided by 255. Again, if the sum equals to 10, the output should be white. If not, it should be black. This way we actually shrink everything. Yes, not much is equals 10, and we'll get to sharp edges. So as you can see right here, this should be my t-shirt, and right here there's not much that lands on 10 or 9 like last time. You just see that. And there you go, nothing. Exponential filter is where we use mathematical algebra. Exponential, it's a built-in code, EXP, and open frameworks. We assign total pixels like before, or a for loop that goes through our window. Then comes where we assign the current pixel to pixel variable, and it's a double pixel, or double data type, where the output for each pixel should be the exponential pixel variant. And that means that every pixel in it should be exponential graded or changed. Now let's see here. Yeah, you can see right here. Go closer. Red eye syndrome. So here, there's another filter. Not much line. Maybe. Oh fuck. Right here. Maybe more line. Yeah. Again, I'm sitting in a kind of black room. I don't got that much light, so some of this filter might be not that much useful, but Yeah, I don't got money for lights. A gamma filter. Same as before. Define our window of web camera. Define our pixels and everything else there's. Red, green, and blue pixels. Then we take a color value and takes it to the power of the value assigned. So if the power of R and gamma, which gamma is 1.2, right here the value used for gamma correction, the output should be this, the gamma thing, and if it isn't greater, if it's lower than 255, the output should be our change color with the gamma in red. If it's above 255, it should just correct itself to 255. So we can make sure that no one exceeds 255, and that way it just turns white. We do the same for green and blue down here, and let's see how it looks like. Whoa. So there's that. Again, to the power of something is a mathematical equation or something that is implemented in the OpenSSH frameworks, and that's something that I actually can mess around with. But it's pretty useful, as you can see. Got the grayscale. Again, we define everything with the grabber as said before. The for loop to go through each pixel, and here in our output window we got red, green, and blue. As you can see, it says 0, 1, and 2. Our output is that, so that's our first webcam, and our input in our second video feed, for that matter, is 0, 0, 0. That way we are gonna remove all the colors, and just each pixel is gonna be white and black. So let's see how that looks like. So on the left side we got me with color, which is our output right here, and the input, the next window right here, is without color at all, only white or black pixels. So that's it. Histogram. Histogram is based on, this one is based on the spectrum from 0 to 255, so that's from black to white. First thing we're gonna do is, again, we're gonna grayscale it down, so it's only gonna be what's it called? So it's only gonna be white and black pixels. I'll follow up right here, and our pixels there. Gonna divide it by 3 because that's what 0 plus 1 plus 2 equals 3. Divided by 3 is gonna be 1, and the output is gonna be grayscale. The most important here is the histogram, taken directly ripped off Georgius. The most important thing here is to draw the actual histogram right here. So we got our line set here. Goes from, as you can see, histogram I divided by 8. That means it's gonna be the height. The length is gonna be from 0 to 25, and the height is gonna be differentiated by I divided times 4, I times 4, everything. Alright, so this line right here is gonna print out our histogram in the bottom, hopefully. Got left side right here, normal picture, right side, black and white, grayscale, whatever you want to call it, where it tracks every single piece of information in each pixel. So there could be a pixel that says, right now there, I don't think there's a one called totally black, but you can see here every pixel varies from 0 to 255 over here. So, and we got this scale where it mostly shows that these are the dominant pixels. We got our inverted filter. Again, everything right cam width, everything video grabber, our for loop, which goes through our cam width times height times 3 every pixel. Then we're gonna take each pixel and invert them. You know, like do a rotation 180 degrees, if you want to call that. We take the pixel value and minus with 255. That way we get the inverted pixel. So it gives us the other pixel in the other end of the spectrum, thus inverting the picture. Let's see here. As you can see, again, we invert everything as it is. So just taking a picture of myself. Got the opportunity to do so. Laplacian kernel. Alright, there's another filter. First off, again, to find everything up here, same old, same old. Then we got a new kernel. Alright, this is a matrix, actually, 2D array. If you wanna, 2D array, sorry. 3.3, 3 rows, 9 everything. A 2D array is created in order to serve as a kernel. This is taken directly from our image processing book. So I don't really, yeah, I just did that. Now we got a for loop again, which is defined. Gonna run through every single pixel again. Where ky is either bigger and kx is either equals to 2 or less than 2, there's going to be added another one. And then we define our Laplacian or kernel from above, right here, this one, into a kernel kx. Again, our for loop like before. This time, instead of just doing the output, we are multiplying with our kernel and ky, kx plus 1 everything, and this should give us our wanted filter, our Laplacian kernel filter. See here again. That way we can detect edges better, but the rest is gonna get blurred out. As you can see here on my right side of the screen, all the edges, especially in my hair, is clearly to see compared to on the left side. Again, this is just so we can edge detect different kind of things. It's a filter you can put on if you wanna use to detect an edge, something like that. Yeah. Again, another mathematical algebra filter, logarithm filter. Again, everything is in the setup. It's supposed to be our vid grabber, on-site pixels, total pixels. Then comes the pixels variant, or like before, where we assign the current pixels to our pixels variable. Our output is gonna be for every single pixel, like our exponential, like we had before. This time we just use logarithm instead of each pixel, and then multiply with 20 for better visibility. So it's pretty much like our exponential filter, except this time it's just with another mathematical term or algebra, whatever. As you can see here, again, another filter used by mathematical terms, or now what's it called? Mathematical, yeah, something like that. Alright, the next three here, we got maximum rank filter, median rank filter, and minimum rank filter. The problem with these are my computer aren't that good to actually run them, but we can look through them and just take it as it is. You can see why. This is where you go through each picture, again using cam height and cam width and stuff like that. It's mostly so you can damage control, if you can say that. If you can correct older pictures who's blurry or stuff like that, you try to use median, maximum, and minimum filters in order to draw up the edges and stuff like that. And that is used by these if statement and these 5 for loops, for that matter. The only thing that differentiates between median, maximum, and minimum filters is the output here, where the values should be changed from either 8 for max, 4 for median, and 0 for minimum filters. Let's see how it looks like. And as you can see here, my computer is terrible, or not terrible, it just doesn't run this median filter that, minimum filter that well. But I did test it on some other computers, my friends and stuff like that. They could run it, but it was laggy as hell and only could produce 2 or 3 frames or something like that. So I know it works, but not that good on my computer. I could simply simplify it somehow. So yeah, there's, and I got minimum, median filter, and maximum. So we can just take the maximum right here. Just look at it one more time. Exact same code as before. Oh shit. Except for the output right here, where the value changes to 8. Like stated before, the only thing you can actually change between each filter is the 8, 4, or 0. 8 for max, 4 for median, 0 for minimum filter. As you see here, doesn't work. My computer is slow as hell and stuff like that. So that's those 3. We got opening, which is the opposite of closing filters. Instead of this time, you start with erosion. You shrink an object in order to eliminate all the edges, filters, and stuff like that, and then you use dilate in order to fill out the holes. So you got like a very sharp picture that way. Got again right here. Gonna turn it black and white. Nothing much more there. By using if green is bigger than blue and so forth, as we see before. The 7x7 erosion, like we saw before, if sum is equals to 49, again, erosion shrinks it. And then we use dilation, opposite work method compared to closing. Closing filter, this is opening filter, where you use dilation in the last end, and the result is going to be something like this. As you can see here, first we normal camera, then we use it for black and white, using if red is bigger and stuff like that. Then erosion, shrink everything down. As you can see here, the comparison, everything outside my background and stuff like that is totally disappeared. And then we use dilation to like fill out the holes and stuff like that. As you can see, my eye has gotten slightly smaller. There's more white and stuff like that. So it's basically what it does. So my hands, alright, you can see it fills up more. it actually, the last image right here resembles the forest more, and that's why I use it. We got optical flow, something our dear friend of mine showed me. Again, goes through, there's nothing particular here. Everything is the same. The most important thing about this optical flow filter is that it doesn't require update, it's more how you draw the picture. So I for loop through everything. Again, we get every single pixel color. I is equal to our frame. Again, R, red, width, get pixel, I plus 0, again, green and blue. Then we calculate brightness instead of the vectors, where we say BR equals R plus B plus G divided by 765. Then we use the HSB colors. Again, BR, as we stated before. Then we calculate sinus and cosine of brightness right here. Then we draw rotated lines based on brightness, and that's right here. And that should give us a pretty funky filter based on red, green, and blue. Alright? How you like that? And the draw lines, as you can see here, everything is sinus, cosine, stuff like that. So they actually turn to define your self. That's pretty awesome. And not define yourself, but they turn to like make the borders, edges. Then we got a pastel color filter, pastel file. Again, nothing unusual up here. Got our for loop. Go through each pixel. Then we're gonna create 9 constants that have a specific value of a pastel. The pastel version of the red, green, and blue. So we were digging after the pastel properties, and we found them. Everything right here. Pastel colors. And then we again red, green, and blue as input. Then we add following right here if statements right here. We are adding the pixels to the values, and then we're going to divide it by 2 to ensure it does not exceed 255 and outputs the pastel filtered image video feed. Again, nothing, as you can see here, define red, green, blue, and red, green, blue all the way down. And as you can see here, our output is going to be red, green, and blue, like stated up before. So there's some constraints or some rules for RGB in our output video. So let's see how it looks. And everything is pastel colors. Yeah. And resize is not that important. It's a small one. Go through. There's nothing much right here. The only thing that matters is our video texture. How we're gonna draw our second window. We're gonna multiply everything with 1.5. And that way it's gonna be bigger. So let's just see here. And as you can see, it's 1.5 times bigger than my original windows. That's also filtered. RGB to normalized RGB. Next filter. Again, nothing unusual. Define RGB down here. Then we're gonna call some new data types. That's my new R, new G, new red, new green, new blue. I'm gonna double that into a data type RGB and RGB is gonna be red plus green plus blue. Then our formula, this one right here, is found in our image processing book on how to turn an RGB into normalized RGB color. Oh, sorry, a picture, image, whatever. But that way, we use that book and then implement it, and our output should be the new colors as defined by the formula. So let's see here, taken directly from our image processing book. And the result is normalized RGB, as you can see on the second window. Nothing unusual. Salt and pepper is sprinkling the image with grains of red, green, and blue. Again, nothing unusual up top here. Again, nothing unusual. We are gonna make a new integer, a variable that draws a random number between 0 and 100. Then if this number, that's the salt pepper, that's what is gonna draw a number between 0 and 100. A new variable of the data type intensity. This is the range where the pixels will keep their original so if you set this number higher, there's gonna be more red, green, and blue sprinkles, dots all over the image. And if you set lower, there's a small chance that each pixel will become that. Then an if statement: if our salt and pepper, the number between 0 and 100, is lower than 5, our intensity, then our pixel is gonna be 0, which is black. And if salt and pepper is greater than our intensity, our salt and pepper, the number between 0 and 100, minus 5, if that's higher, it's gonna be white. Yeah, so let's see how it's gonna be. Oh, look like. Oh. Yeah, as you can see here, there's a lot of sprinkles. Different kinds of. And if we just intensify it, it's just gonna 50 instead. It's gonna be a lot more. Yep, so you can barely see me, or I can't. Satyrion folder. Again, nothing unusual. For loops to go through the web or the image. Then an integer is created with a value of -50, which will be added to our red, which is declared below. So we've got red, green, and blue. So if our -50, if the add Satyrion is, as you can see here, -50, if that's less or bigger than 0, and if R was red, declared up here, is bigger than 255 minus add Satyrion, which is 205, R, our red color, should be added -50. If not, if add Satyrion is less than 0, which it is, R should be 255. That way we actually pose a limit to the value of R by add Satyrion. Same goes for the parameter. If the parameter of the first sentence is not met, as you can see here, you should add a Satyrion. If it's not met, then there's another if sentence or to actually back up, and this is the more important one, so we make sure that everything is going to be that way, and that way we can change R to becoming more sorry, I just got out of it. Alright, so this left if there is the point mark, left fail safe for the point mark. And the way we're gonna remove all the red color into a more ice cold blue, as you can see here. So only green and yellow that's done, and as the red is decreased with -50, as stated here, as we add Satyrion, which is -50. The last filter, oh shit, is the sepia. To make everything brownish, old school. Again, nothing in particular. Then there's common use sepia. The three values that are the values of the color sepia posed as cursor that will be later used in the output row. Again, because there's a specific type of sepia. That way we found it through through the internet. Define red, green, and blue pixels again. Here we are gonna add the constant to the pixel value and then divide it by 2, so we can ensure again, like before, that it doesn't exceed 255. So that's what we're gonna do. For every output, we're gonna take R plus sepia R, R plus sepia G, and R plus sepia B. That way, we will create our sepia filter. Yes, you can see everything is pretty brownish, red, brown. As red is. You mix black and red together, you get brown. Oh, never mind. But that's it. My last filler. Yeah, I hope to see you again or not. It's been fun, but now I'm gonna go be sick. Have a good day.